So the very first part of a compiler is concerned with lexical analysis, or simply called scanning. And as we've seen, the task of the lexical analysis is to take the character input stream and transform it into some sequence of tokens which are annotated with the meaning of that token. So what the compiler sees when you read a file is simply a sequence of bytes here. So it might be 72, 101, 108, and so on and so forth. So by convention, we just map these characters or these bytes to sort of characters. So the convention we are using here is the so-called ASCII encoding. ASCII is just short for American Standard Code for Information Interchange. And this is the most common code used on most computers today. So ASCII would just define that the first byte, 72, would correspond to a uppercase letter H, the second one, 101, corresponds to an E, the third one and the fourth one, 108, correspond to an L each, and so on and so forth. There are other mappings or character encodings which have just different assignments of available characters to the numbers they are represented with. So a compatible encoding, which extends ASCII to use international characters, different character sets like Japanese or Chinese, is Unicode UTF-8, and there are also very ancient other incompatible encodings like so-called EBCDIC, the electronic binary code for digital information interchange, which is used on very old but also on relatively new IBM mainframes still today. So if you have program source code written in one of the incompatible encodings like EBCDIC and you want to compile it using a compiler, well, written for ASCII encoding, you would have to somehow change the encodings. But luckily, most of our computers today simply use ASCII, so we'll go with this. So on the input level, when we read our input source code file byte after byte, the input program is just a bunch of bytes, one after the other, and this doesn't have any structure. So we need to put some structure into it. So we can start with a very naive approach to scanning. So the naive approach would be to just use a scanner to read letters one by one. So when we want to look for a keyword called while, which is indicating that we want to start a loop, we would start to look for a W, for an H, for an I, an L, and finally an E. Now, this is pretty inconvenient, because when you write a compiler that has to detect this pattern every time the program wants to start a loop, then your compiler has to start, check, oh, is there a W? Yes, hooray. Is there an H? Oh, fine. Is there an I? Yes. Is there an L? Yes. Okay. And now finally we need an E, but oh no, the programmer has decided to call a variable wilf. So it's not a while. It's wilf, and this is something else. It's not a control statement of our language. It's just maybe a variable name. So it's not a loop. So we have to go back to the start, to the first W, and start from scratch because our assumption that maybe a loop was coming was wrong. And this can be done, but this is very much lots of overhead. So we want to somehow avoid this overhead and do it in a bit more intelligent way. So what we want to do is to identify syntactical units. So if it were a natural language, we would be able to identify single words. So the better approach is to group the letters of your input text into meaningful units and then let the compiler operate on those. So we have this input text here, an I, an F, an opening bracket, then WHILF or WILF, then two equal signs, and so on. And now we can already do some sort of annotations in our head, and this is indicated by colors here. So you see we have split our input character stream into different parts having different properties, and we use color coding to identify the units. So everything in blue is a keyword or punctuation, like our if here in front. Everything in red is a delimiter of group, like our round brackets or curly brackets here. Things in green are variables here, like our wilf, because it's not while, it's wilf, and our x. In purple, there are operators like our equals comparison and our assignment operator equals. And finally, in orange, we have numbers like our number 2 and our number 5 on the right hand side here. So if we have a tool that splits our input character stream already in these parts that have a certain meaning, the rest of the compiler has less work to do in operating on all of these input data objects. So what's the use of this coloring we've applied? Now we've already seen the first line we've colored. So the question is, if we have something that's different, a piece of a different input code, how would we color that line? So we have this line in the middle here. While a is less than 42, a plus equals 2. And the interesting thing is, if we apply the rules from the previous slide again, we get the line here. So these two statements have completely different meanings, but we see the coloring as absolutely the same. So it has the same syntactic structure, or sequence of color in our case. We'll talk about this structure later. First, we'll just talk about what enables us to actually split our input character stream into these parts and to assign these colors. And later on, we'll talk about the relations of these colors, so how these come together in order to make a meaningful program. So to start our discussion of scanning, so the first part of our compiler, it's good to have some definitions so we know what we're talking about. So the first thing we're going to define is a so-called lexeme. Lexemes are the units of lexical analysis, or simply the words in our input language. And they're like entries in a dictionary, like house or walk or smooth. Then we have tokens. Tokens define classes, so they're units of syntactical analysis. So they're like units of a sentence in a natural language, like a noun or a verb or an adjective. And you see there's already a relation to what you learned in grammar of natural languages in school. And finally, we have semantics. So the semantics is the meaning of something. There is no unit for it. You cannot count it or something. It just implies what the program is actually doing. And the semantics is somehow similar to explanations in the dictionary. So a house might be defined as a building which somehow someone inhabits, or to walk is the act of putting one foot in front of the other, and so on and so forth. So essentially, with semantics, we describe whatever unit we're going to talk about is actually going to do. So when we have lexemes, we want to classify each and every lexeme into its given class. So we have certain lexemes that have a fixed meaning here. And these are keywords or reserved words. So these are the words making up the structure of our language. So we have, for example, if, while, for, but also something that wouldn't ordinarily in natural languages be recognized as a word, like the equals equals operator, which is also reserved. You cannot name a variable equals equals. Most languages forbid the use of these reserved fixed meaning lexemes as identifiers, so variable or function names, which makes the source easier to parse and which makes your program less ambiguous. Then you can also have classes with countable infinite instances. For example, we've seen the class number before. So a number can be a 1 or a 2 or a 3 or a 65, 5, 35, and so on. So we want to have a single class encompassing all, for example, all integer numbers in our code. And we don't want to create a class for integer number 1 and integer number 2 and so on. So if we encounter something like this, which can have arbitrary many characters here, like it can have 1 character for the 1, or it can have 5 characters for the 65, 5, 35. We all want to assign these to a class integer number, for example. And to do this, we can use a tool that's called a finite automaton. So what we require is to have a mechanism to identify classes of words. So not just single words, but we want something that takes a character sequence as an input and outputs the information which class actually does this sequence of characters belong to. So for example, we want to have a mechanism that recognizes real numbers. And we can start with an informal description of a real number. So a real number starts with one or more digits, optionally followed by a decimal point, followed by 0 or more digits. We're simplifying it a bit here, so we don't indicate negative or positive numbers, so we don't have a plus or minus sign here, for example. The formal approach to do this is a DFA, or deterministic finite automaton, and the example for a real number is given in a directed graph below. So there are very many representations of DFAs, but this graph representation is very easy to follow because you just follow the arrows in your graph representation to figure out what's going on. So we start off with an initial state. So our automaton starts at a state as 1. And an automaton can always be in one and only one state at the same time. So we start off with as 1, and then we start to read the first character that comes along. And if this is something between 0 and 9, so notice this notation, everything in square brackets means it's a range of characters, so it's somewhere between the character 0 and the character 9, so it's all of the digits we have, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we proceed to the next state. Now this state has a double line around it, which means it can be a so-called accepting state. So an accepting state is a state in which the automaton gives a meaningful output, and it says, yes, I have recognized a valid real number. And of course, a valid real number can be a number 0 or 5 or 7. So this is fine. So, well, a number containing just one digit is obviously a valid real number. But of course, we can have numbers with more digits. And that's why we have this arrow going back from state 2 to state 2. So we can have the number 1, 2, 3, 4, 5, which would go from S1 to S2 for the first digit, the 1. And then for all the remaining 2, 3, 4, 5 would go over here again and over here again until it encounters something different. So the only valid other thing than a digit in a real number is the decimal point here. So when it encounters a decimal point, it can go to a different state. And this is state S3. And in S3, we can specify the digits after the decimal point. Now note that S3 already is also an accepting state, so a decimal number of 9 point would be a valid real number here. So if you want to change this and only have something called 9.5, but not 9 point, you would need to change your grammar around to be able to accept it. And that's maybe an interesting thing to think about, how you have to do this. So a DFA is a very simple representation of a number of rules that actually lead to something being detected as a valid sequence of whatever this DFA is built to recognize. In this case, real numbers. So the question, of course, is what happens if we have some other input like an A? Well, then it's obviously an error, so our automaton cannot accept this input. So we need to look somewhere else, maybe in a different automaton, recognizing identifier names. So to give a structural overview of DFAs, we've already seen these are represented as directed graphs. These graphs consist of a number of vertices, states here, S1, S2, S3, and a number of edges, our arrows here, connecting the states to one another. There is an arrow going into our DFA that does not have a state at the start. This is our start state. This just indicates whenever you want to detect something, you always end up in state S1 automatically here. And then you have the transitions, and transitions are usually annotated with the conditions. So what you do in S1 is you read a character, and when this character fulfills this condition here, it's between 0 and 9 inclusively, then and only then can we proceed to the next state. And finally, we have the accepting states here with the double lines around them, which means whenever we ended up in this state and, for example, our input ends, for example, so our program text ends, then we have recognized something that's a valid token in our grammar. So a very formal definition of a DFA is to say a DFA is a so-called 5-tuple consisting of a finite set of states called Q, a finite set of characters called the alphabet sigma, then a transition function which takes the current state and the character that's read as an input and outputs the subsequent state of your automaton. This transition function is called delta here. Then you have a way to indicate the start state. So there's one special state Q0, which is one of the states in your automaton, which is a start state. And then you have a set of states, F, you can have 2 here, which is a subset of your overall set of states, and this is the set of accepting states. So when you write a formal definition, you can transform this DFA graph representation to this representation here on the right hand side. So this graph has states S1, S2, S3, which we indicate as Q. It has an input alphabet of just digits 0 to 9 and the decimal point, which is sigma. It starts at S1 and the accepting states are S2 and S3. So the big question is, what does our delta function look like, this transition function? Now, this transition function is just a mapping of an input state, so the state we're currently in, and an input character, so the character we're reading, and it gives an output state. And a very simple way to represent this is to just write it down as a table. So this delta function, for example, tells us if we're in state S1 and we read a 0, we proceed to state S2. If we're in state S1 and we read a 1, we also proceed to state S2. Now, if we're in state S1 and read a decimal point at the beginning, there's nothing there. We don't know what to do. So we'll take a look at that later. And well, you can see this is a representation that works very well. This is very valid for something a computer can operate on, because it only has to look up the current state, which is stored in some variable, and it has to check what is the current input character, and then it can just look up in your table, okay, we're moving to a following state, for example, S2 or S3, somewhere here in our automaton. So this is a representation of a delta function as just a table of values. And we can usually write it as such a table of values because both the input alphabet and the number of states in our automaton, that's why it's called a finite automaton, is finite, so we don't have any infinite number of elements there. So it's just representable as a simple two-dimensional table here. So let's look at an example for a transition. So we want to recognize this input character sequence 42.23. So we have our automaton representation here and the transition function again represented as our table up here. So what we do is we start in state S1 here, and in state S1 we read the first character. So we read a 4. So we can look it up in our table. We are in state S1, we read a 4, so we have to end up in state S2. In S2 we read our second character, the character 2, S2, character 2, we'll stay in S2. Alright. So we're again in S2 and we read the following character, which is the dot. So this dot our decimal point. We can look it up. S2. We have a dot. So we need to move to state 3 now. Okay, we change to state 3. And then finally in stage 3, we read our fourth character. We read the character 2. S3. 2. We stay in S3, obviously. And again, we read the final character, the 3, which also means we stay in S3. Our input character sequence is ended here. So we're out of characters to parse. We're in an accepting state, so we have successfully recognized a real number 42.23 here. This is the end of the sequence and we're happy. Now, as we've seen, this table has some open spots here. So what happens if we are in state S1 or in state S3 and we get a dot as an input? Now that's an error. So we cannot have a decimal number called 0.123 and we cannot have a decimal number called 1.23 something. The error state is often omitted in DFA descriptions to make this more simple. So only the valid transitions in your DFA are actually noted here. The invalid ones are implied. All non-indicated characters just lead to an error message here. Now, how do we implement such a DFA? A DFA is just a number of decisions you can take. So we can write it as a piece of C code. And you can do it a hard way. So we have a function scan real number here. And this scan real number function can return an error or can return success. And scan real number now starts. It defines variables for a character. It defines the states we have as 1, 2, 3. It uses an enum in C to make it easier to assign symbolic names. You could use defines for this, but enums are the more elegant solutions. And you have another enum state type, so one variable containing one of the values of the enum. That is initialized to S1, which indicates that our automaton starts at state S1. And now we have an endless loop here. In this endless loop we call the getCharacter function. This is a Unix system function which just returns the next character of the input. Now if this character is the end of file, so we don't have any characters left in our input, we break out of our while loop and we end up here. Here we check if our current state is S3 or S2. If this is not the case, we are not in an accepting state but don't have any characters left. So we just return the error. But if we're in either S2 or S3, we return success. So we know what the automaton does when it ran out of characters. What does it do when it has characters left? So we're here. We read our current character here. It's not the end of file. So now we have a switch statement and check in which state we currently are. So this switch statement actually implements your automaton. So it checks, are we currently in S1? So this current variable indicates the current state. Is it S1 or is it S2 or is it S3? So if we're in S1, we now implement the transition to another state in the automaton. So if we're in state S1 here and our character is between 0 and 9 inclusively, which is our transition here, we'll set our current state, so the state our machine should take in the following step, to S2, which is our transition here. If there's something else that we read in S1, we can immediately return an error. If we're in S2, so we set our current state to S1, we run to the end, and we run through our while loop again. So our next character that comes, we're in S2, for example. Here again, we check if we're between 0 and 9 with our input character, we stay in S2. Otherwise, if our input character is a dot, we move to S3. And otherwise, well, we failed. And finally, in S3, we check again. As long as there are digits incoming, we'll stay in S3. Otherwise, we'll indicate a failure, and that's it. So we only get out of this loop when we have found that there's an invalid input character. So we have, for example, this and this transition here. Or if we reach the end of our input, and when our input ends, we can check if we are in one of the accepting states at the point in time our input ended. And if this is the case, we successfully parsed or scanned an input character sequence, and if this is not the case, we indicate that there is some sort of problem. Now, as you can imagine, this is a very simple example. So if your DFAs get more complex, then this piece of code implementing the DFA gets really, really hairy, because you have many switch statements, you have many nested if statements inside of there to check which follow-up state there is. And so this is really hard to write, and this is really hard to maintain when you want to make changes. So you can also implement a DFA in a more simple way, which makes it easier to change things around and which makes it easier to maintain your program. And this is shown on this slide. So this implements a table-driven DFA in C. We've seen the representation of our graph, which we implemented bit by bit on our previous slide. Can also be identical to this representation in a table here. So what we do now is we map this table here to a data structure. This data structure has a number of entries. So this is called delta because it represents our delta function. And for each of the states, it has one line. And each of these lines has a number of entries here, which represent the subsequent state. So essentially, it's just writing down your table as a C data structure here. So each row consists of all the follow states for a given state, which makes it very easy to change, and it makes it easy to interpret. So if we now write our scan real number function here, we again have our character C as variable, and then we start an endless loop to scan our input text. We read the character again, and as before, if we reach the end of 5, we just break out here and check if we arrived in a valid state. Now the difference is that the only statement left here is this one in red. So we set our current state by looking up in our table, first the line in our table that's equivalent to the current state, like the first line here, for example. And then inside of this line, we check what's actually the line corresponding to our input character, like a 5 here, like we have S1 and a 5, and we return S2 as our current state. So this makes it easier because this program here doesn't have to be changed. The only thing you have to change is what's shown on the left-hand side here. So your alphabet, if you want to change your grammar, for your automaton, the states, and of course the state transition table. Two things remain open questions here you should think about. There's a function lookup of C. Think about why this is needed and how would you implement it. And there's also a potentially dangerous subtle bug in the code. And of course the challenge is, can you actually find this? We'll discuss this later. So we've seen two ways to implement a DFA in C. The first way is to write a large complex bunch of switch and if statements. The second one is just to write down a table and to have a very simple program doing the scanning. But there's also another way, making life easier for you, because programming a very good recognizer or scanner with this logic you just implemented ad hoc is complicated and error prone, especially if your language gets more complex. Writing it using tables is a bit easier, but you have to write very boring code because you just have to type down tables. And if there's one mistake in your table, well, it's hard to find, it's hard to debug. So people, of course, had these problems before, so they were thinking of better ways to do it. And these ways are an important part of the compiler toolchain nowadays. We have code generators for scanners. So these code generators take a description of whatever language you want to recognize here, and it automatically generates C code from a simple descriptions. So you specify the word classes as so-called regular expressions. You then let a program write this large table of states automatically, which includes all of the expressions, and we'll take a closer look on how this works next week. Thanks for today, and see you again in our next lecture.